we've done electronic elements before, right? We did them for the first 6 weeks in this class. So this is a review of electronic elements, and it's meant to be, I considered just skipping it and just like including the notes on it so you can go back and read it, but I want to go through them quickly because we've seen all of it before, but I want to frame it in the same way we just framed the mechanical system elements, and then we'll draw these analogies at the end of today and then on Wednesday too, between, well, among, I guess, these different systems. So we'll do the electronic systems like really quickly. We're going to move through these, but I think that it should be fine because we've seen them all before. Nothing new here. And actually, we're only going to look at the sort of simplest of the electronic elements we consider. We considered more complex ones than we're going to consider in this set of notes. So we now review a few lump parameter elements for electronic systems. The current and the voltage, I and V, are the power flow variables, and so if you take the product of them, you get the power into a system element. Voltage is always understood to be between 2 points. Oh man, between 2 points, man, jeez. Brutal. 2 points in a circuit. If only 1 point is included, the voltage is implicitly relative to a reference voltage called ground. The magnetic flux linkage, lambda, is the integral of the voltage. The charge is the integral of the current. We now consider two elements that can store energy, called energy storage elements. What are those two going to be? What are the first two we considered?
Capacitors and inductors?
Yeah, exactly. A dissipative element, what was the one we did? Resistors. And then two source elements. What are the two sources? Yeah, voltage and current sources. We're going to look at these, but notice that this is the same thing that we just did, but for electronic systems. So the storage elements, dissipative element, and source elements. So the capacitors first. They store charge on plates and energy in an electric field between those plates. A capacitor has a constitutive equation, meaning having this relationship between charge and voltage constitutes what it means to be a capacitor, a linear capacitor, at least an ideal capacitor. And the time derivative of that gives us the elemental equation, the relationship between the voltage and the current. And we noted before, and so this is a lot of repetition, that this is a differential equation. There are different types of capacitors we're familiar with, bipolar versus polarized. In lab, you guys did an RLC circuit, and you guys saw that second order response with the resonance that emerged in it, which is pretty cool. You guys used a bipolar or unpolarized ceramic capacitor in that lab, as I recall. Is that right? It's because it's AC, right? So you gotta apply voltage both directions across it, so you can't use a polarized capacitor. You can, but it's not recommended. Doesn't work very well either. Yeah, so that was stuff that we learned already about capacitors. Inductors are defined as being elements that have a monotonic relationship between the magnetic flux linkage and the current, with the linear case being the ideal one, which is pretty commonly used as the model, so lambda equals Li, where L is defined as the inductance. And if you take the time derivative of that, you get yourself the elemental equation for an inductor, di dt equals 1 over Lv. And these inductors store energy in their magnetic fields. Okay, so that's all stuff that we've seen. that we like. I like at least. I don't want to presume. I feel like we might all like it. Seeing some doubtful looks. Resistors dissipate energy from the system into heat, right? So their elemental and constitutive equation is that V equals IR, at least for a linear resistor. And that's our favorite element for sure. Sources, also known as supplies, supply power to a circuit. Two primary types, voltage and current. And then I talk about ideal voltage sources, so sources that can supply whatever current you specified, and they will happily change the voltage to make that happen. Whereas an ideal voltage source or an ideal current source supplies whatever current required and specified, and will supply whatever voltage is necessary. A real source model we discussed is for a voltage source is a series resistor with an ideal voltage source, and a real current model, pretty good model, is a current source in parallel with a resistor, like that. So that was, we just kind of did it, but that was what we've been doing, and we're all pretty familiar with it. So now we're ready to start drawing analogies. So let's do that.